We'll finish off this section in Python data types by looking at Python libraries and something called turtle objects. Core Python programming language comes with data types such as ints, floats, and strings, and it comes with functions like min and max and absolute, but it's kept small for efficiency and complexity. However, there's something called the Python Standard Library, and it consists of thousands of functions that you can use and various classes organized into components called modules. There's actually more than 200 built-in modules for the Python Standard Library. These libraries support such things as network programming, web applications. For instance, it's easy to use this to parse HTML web pages. GUI, the graphical user interface development, databases, math functions, and random numbers. So we're going to start by looking at the Python library, and in particular, at first, the math function. In the Python Standard Library, the math module is called just math. And to use it, you first have to import it. So we'll take a look here at how we do this. It uses an import statement and the module name. We can do a directory of the module to find all the functions that are contained in it. So we can see here there are things like tangent and sines, logs, square roots. We're going to look at using the square root function. Now, square root is a function, sqrt, and let's suppose we want to find the square root of 3. Now when we try to execute this, we're actually going to get an error because it can't find the square root function. It only looks in the core of the Python language. So we need some way to tell it that square root's in the math module. We do this by typing the module name first and then using the function. These are some of the functions here, the common functions that you'll use in the math routine. If you want to find out how to use something, you would use the help, built-in help feature. So we want to get some help on the cosine function of the math module. And here we go. Now it's pretty terse, but once you use it a few times, this will jog your memory. The ceiling and floor functions are used with plus and minus integers. We talked before about converting, say, a float to an integer. So that conversion is just done by dropping the decimal point. Ceiling and floor are a little different. Whoops, need to put the module name. And so what ceiling does is gives you the integer value which is greater than the float that you've got. So here we get 4. Minus 3.4, what do you think that would be? That's minus 3. So if you look on a number line, the integer that is greater than minus 3.4 is 3. The floor works similar, but it's going to find the largest integer that's actually less than what's specified. So this should return 3. So this is the largest integer that's less than minus 3.4. Whoops. And we should find that's minus 4. So it's called the ceiling and the floor. Now we'll see how well you do. Write expressions for each of these 3 problems. And do it in your Python shell. Pause the video and then move forward. With the first one. If you remember your Pythagorean theorem, a squared plus b squared equals c squared, where c is the hypotenuse. So what we have here is c is going to be the square root of a squared plus b squared. So we want an expression that'll compute the hypotenuse, which is c here. Well, if we look at what we've done here, we've defined an a and a b, and we've computed z, which is the square root of a squared plus b squared. So let's see how well this works. We should get 5 here. So if I just hit Z, we get 5. For the second one, we have the area of disk, which is pi r squared. So if we have a radius a, we'll say our radius is 3. So let's look at our example here. We would say r equals math.pi times, put a space for readability, a is a radius, a squared, and if I print r, we'll get 28.27. So that's our expression there. In the next one, we want to find to see if a point x and y is inside a circle of radius s. So let's draw this here. We've got our radius r. And we've got some, let's suppose this is our coordinate system. Right at the center. And so we've got a point xy somewhere, x units over, y units up. We want to see if that's inside a circle. Well, if this is x and this is y, what we need to do is find the length of the hypotenuse of that. And if the hypotenuse is less than r, then it's inside the circle. That is, the length of this hypotenuse is less than the radius. So what do we need to do? Well, we need to compute the square root of x squared plus y squared, similar to what we did up in the first part. And we need to see, is that going to be less than r? So we'll do that down here. And we're going to show some features of the idle environment as well. Maybe we don't want to type this again. So let's suppose we've defined a and b as 3, and let's suppose we define a radius as 6. And we want to see if x and y, we're going to put it as a and b, which is 3, 4. We want to see if this point is inside the circle. Well, we can compute the hypotenuse of a and b using this function we've done before. And in idle, if we just put the cursor at the end and hit the return key, it takes this and copies it and puts it down here, which can be pretty convenient because now as I execute it, I can find what z is. And so I want to find out if that is less than my radius. So my expression, if I wanted to do it all in one statement, would be this. And let's use x and y. So we'll say x equals 3, y equals 4. So I want to find the hypotenuse of that point. And notice that if you pause, it will bring up all the functions that you can use in the math library. So you could actually choose from one here, if you didn't know. I thought you could. That did not quite seem to work. So apparently it shows you the functions, it doesn't type those in for you. So we want to first compute the hypotenuse here. And then we want to find out, is that less than my radius? So here my radius is 6, so I should get a true answer. So what this should return is a true and false depending on if x and y is inside a circle of radius r. Let's look at another math library for working with fractions. So the fraction library needs to be imported, and how a fraction is represented. So what we're going to do is we're going to add the fraction 1/2 plus 3/4, and we want to get the result as a fraction. So we've imported fractions, and the way to define a fraction is a is going to be the first fraction. We need the module name fractions dot, and we're going to use a function called fraction, and that takes two arguments or inputs. The first is the numerator, the 1, the number on top. So it's going to be the 3, and the denominator is 4. So we've defined the second fraction. We're going to have b, and we're going to define this as the first fraction, which should be 1/2, 1 comma 2. Now, if we just type it, we'll notice that's a fraction. If we look at the type that a is, it's of the class from the fractions module called fraction. So using these new modules, we can declare new classes. Now, what happens when we add these new classes together? Well, what we want to get is a new fraction. So if we hit C, we'll see that the answer should be 5/4. Now, fractions can be very large. So let's do this. If we have a floating point number we're raising to a large power, it is so small we just get 0. We don't get any precision at this point. But if we treat this as a fraction, so instead of 0.5, I'm going to say that's a fraction 1/2, and now I'm going to raise this to the 1075. And that will work actually in most languages, but not here. No, I mistyped it. Sorry. Fractions is the module name, not fraction. So these are the type of errors you'll run into using Python. So what we get is a fraction of 1 over a very, very large number. Sometimes the question is, why wouldn't we just use fractions instead of floats? Well, fractions are actually pretty slow to execute, and so floats can be more efficient. Okay, so that completes our work on as an introduction to the Python standard library. We're now going to look at something called turtle graphics and turtle graphic objects. Where do these turtle graphics actually come from? Well, the history is back in the 60s, and a turtle was actually a little robot created by Seymour Papert, I think, of MIT, the Media Lab, the Massachusetts Institute of Technology. And it was a device which is designed to teach children how to program. And what it was, it had a little pen underneath of it, and children could learn to program this turtle to draw little objects. Here we're drawing a teddy bear. And the idea was to introduce people to programming type of think. It's designed to illustrate some of the basic programming concepts, and so we're going to cover this because it's part of the Python language. Turtle graphics, as we mentioned, was invented in the 60s, and it was part of a language called Logo, designed to teach children how to program. Simon Seymour Papert. And it's a vector type of drawing. So we have a turtle, and think of a turtle as having a pen on its tail, and you can direct the turtle to go left or right or forward, and as the turtle goes, it draws a line. And after you've given it a series of instructions, it will have a drawing on the page. So we're going to look at making a turtle drawing here. So to do this, you first need to import the turtle module. And then we need to what's called instantiate a screen. Make a screen that the turtle can draw on. So this is a function. And there's my turtle screen, which I'm going to try to resize. I may not be able to, but so you can see that screen. We'll sort of flick back and forth between the screen. Now we need to create an actual turtle. So we need to instantiate a turtle, create a new object. So we need the module name from the turtle module. We need to run the method called turtle, which will create a new object, a turtle object. That's T. So the screen has got the name S, the turtle will have the name T. We go back here, our little turtle is represented by an arrow. Now we want to move the turtle and have it draw something. So let's suppose we say T dot, so T is our object, our turtle object, dot forward 100 pixels. And we'll take a look here and see, it's moved and drawn a line 100 pixels to the right. So we can go T dot left, 90. We're going to make a left turn, and you see that the turtle has rotated here and is about to go left or upwards here. Now we could instantiate a new turtle. So let's look at our second turtle. So we see we've got a new turtle, and when it instantiates a new turtle, unless you tell it different, it goes right at the origin or the center of your drawing window. And we're going to give it a bunch of instructions. So we're saying turn left, go forward 100, move the T turtle forward 100 as well, and then rotate the U turtle right 45. So let's see what the output of all this is. So this turtle has turned, it's drawn, and we've also, so this is the T turtle here, it's moved, and this is the U turtle. So we can draw fairly crude vector diagrams using turtle graphics. But really this is just designed to show you some of the programming elements and get you familiar with seeing immediately the results of some of your programming steps. These are most of the commands that you can use with the turtle. You can have what's called a pen up and pen down. So if you put a pen up and you move the turtle, then it won't actually make a line, it'll just move to a different location. There's a tutorial, a turtle tutorial in a document on the website. You should read that and then do the practice exercise in that document.